Hello, everybody. Welcome to Chapter 11. This is the chi-square distribution. And the chi-square distribution is helpful for us when we're looking at data represented in categories. So days of the week or months, things like that. And we have some symbols here to represent the chi-square distribution. This is x is represented with x squared, and then df, which stands for degrees of freedom. And our degrees of freedom is going to depend on how the chi-square is being used. So there's a few different ways to calculate it. But the first part, degrees of freedom, we're going to calculate it by just taking our number of our categories and subtract 1. We have a few different, the more advanced ways are using the average. We'll talk about that later, not right now. So the rules for the chi-square is it's a non-symmetrical and skew to the right curve. So it has a little extra tail on the right-hand side. There's a different chi-square curve for each degrees of freedom. And the test statistic is always greater than or equal to 0. And here we have some, when our degrees of freedom is bigger than 90, or some more specific things here. Degrees of freedom bigger than 90, the chi-square curve approximates the normal distribution. So it just turns more towards that curve. The tail kind of goes away. And then this is talking about a specific example where the degrees of freedom equals 1,000. Well, we're going to talk about that, not on this slide. We'll do it in a future lesson. So we want to determine, in this type of a hypothesis test, determine whether the data fit a particular distribution or not. So for example, you may suspect your unknown data fit a binomial distribution. So you use a chi-square test, meaning the distribution for the hypothesis test is chi-square to determine if there's a fit or not. And the null and alternative hypothesis for this test may be written in sentences or be stated as equations or inequalities. Sometimes they're just a little bit easier to write in sentences because it's, we don't have variables and defined for each of them, which we could do, but it's just easier sometimes to write it out, which is okay. Here's our main statistic for the chi-square. And it looks a little complicated at first, but it's really not too bad. So O is the observed values. So we take our observed values and we subtract the expected values. That's from theory. We'll do this in just a moment. We square those numbers and we divide by the expected value for that one. And then this just stands for we take the sum. So we add up all those numbers. And we're going to get to that. We're going to do that in just a moment. And our degrees of freedom, as I said earlier, take the categories minus 1. Okay. So here we go. Let's do an example. We're going to do this one by hand and then use a calculator to check the p-value. So we want to know which days of the week employers are absent in a 5-day work week. Most employers would like to believe that employees are absent equally during the week. But, right, I mean, we could all probably think that Friday would be a more popular day, and maybe Monday too, take a longer weekend. But for whatever reason, this employer believes that the employees are absent equally. Suppose a random sample of 60 managers were asked on which day of the week they had the highest number of employee absences. The results are shown on the table. For the population of employees, do the days for the highest number of absences occur with equal frequencies during a 5-day week? So I'm testing to see if these days are equal. And here we have our absences. And as I suspected, the Monday, Friday, the weekend days are popular to be gone. Days closer to the weekend. So here we write our null and alternative. Null is the absent days occur with equal frequencies. They fit a uniform distribution. And the alternative would be the absent days occur with unequal frequencies. That is, they do not fit a uniform distribution. So to calculate this, we'll go back to our formula. We take the observed minus the expected, then we square it. So what we need to do is calculate the expected number of absences. And this data was for 60 people. We can add this up, you get 60. So we have 60 people, 5 days a week. So assuming they were all equal, they would all be gone, 60 divided by 12, 60 divided by 5, so 12 days each day of the week, which we know probably isn't very true. But we'll see if this is statistically significant enough to say otherwise. So we Go ahead and we take those observed minus the expected. So the first one, Monday, 15 minus 12, 3. There's 3 extra days here. Wednesday is minus 3 because there are 3 less than expected. So we take those observed minus the expected and we square them. Then we take that and we divide by the expected number of days or expected value for that day, which isn't always the same number, but for this one it is the same number. 12, 12, 12, 12. So we take all those and then we add up all of those numbers. So all those 0.7, they all happen to be 0.75 this time. We just take them and manually add them, adding the 0 to, we get 3. So that's our test statistic, 3. Our degrees of freedom is number of categories, 5 days, minus 1, 4. So we use this information, test stat 3, degrees of freedom 4. So I take that into my calculator, test stat 3, degrees of freedom 4, tested at the 0.05 level. And it tells me the p-value is 0.55, so not significant. So this is actually very common. So apparently there's not enough data to support our problem. So here we go. We say if we decide to not reject the null hypothesis, this means we found the null hypothesis to be true. So we need to conclude it properly. So at the 5% significance level, there's not sufficient evidence to conclude that the absent days do not occur with equal frequencies. Okay, there we go. So that's our first example, and I'm going to stop this video there and I'll make another video for the next one.